We start again. Just wanted to say something. Compared to the other days, you had one full day about remote sensing for forestry, remote sensing for agriculture, etc., etc. Today we have just this morning about marine applications, and we have theory. We don't have time for practicals because this afternoon, as you know, we are going to do something else. So I asked Amalia to put in the chat links to other additional material and practical exercises about radar for oil spills or ship detection. We have, for example, developed with Copernicus, Rus. It was a service running for 3 years. We had webinars also with practical exercises using SNAP for ship detection and oil spills. So Amalia will put in the chat the link to those. So if you are interested in the subject, I really advise that after listening to the theory, you also look at the exercises, because otherwise you will not fix this concept if you are not applying what you learned also from the practical point of view. So this is for the practicals. And then I also asked Amalia to put a link to the radar MOOC, the Massive Online Open Course that we did, because I think that also there is something about radar applications to oil spills and ship detection. So please have a look at the chat.
Yeah, so what I was telling you about here is what is the physics behind the observation of oil spill with SAR. So we have the oil that is smoothing the ocean surface, which means you receive no backscatter, or you receive less backscatter. And what is happening is here called, so over the ocean surface, you have the so-called bragg scattering, and on oil, you have a departure from bragg scattering. In which conditions are you able to detect oil with SAR? So when you have here low wind speed, so we have seen that wind is something important to generate the roughness over the ocean. If you have low wind speed, you basically have a flat ocean surface. It doesn't matter if you have oil or not, so everything is flat, so everything will be having low backscatter. And this, so when you have moderate wind speed, then you have the generation of the roughness of the ocean waves. And so if you have detections, it's mostly probably pollution, soil pollution. And the other limit is when you have very high wind speed, because when we have very high wind speed, the oil start to mix in the waves, and so you don't have this smoothness anymore, so you cannot detect the oil. How they look like oils in SAR images. So we have talked about operational discharges. So you have one example here of tank washing procedure, where you have the ship that is tracked by the automatic identification system. And then behind you have this trail of dark, this dark line, which is oil. Then you have like from platform source pollution, you have rounded curvilinear shapes of oil. And then you have like accident, which are, in case you have an accident, it can be discontinued patch, so you have different oil patches floating over the ocean. And then you can also have rounded shape when you have a platform accident like here. Just a little information about with the oil type. So there was some experiment to provide how the oil type influence the SAR oil spill. So you see like light fuel and heavy fuel. So when you have a heavy fuel, you usually, independently on the wavelength of your radar, you receive a little bit more backscatter, and And you see also the different polarization, what was measured. Here is also a little bit about the wavelength influence. So you see that different frequency or wavelength. So who doesn't know about frequency and wavelength? Okay. So the radar needs to transmit the pulse using a certain frequency. And frequency and wavelength are reciprocal. So it's one over the other. So you either have high frequency, which means the pulses are very short wavelength, or you have low frequency with longer wavelength. So the acronyms here are L, S, C, X, KU. These are the usual frequency bands, which range from centimeters wavelength to tens of centimeters wavelength to centimeters wavelength. For example, I show here, like you have like in X band, you have something between 1.8 and 5.4, 4.5 centimeters. So the different frequency or wavelength will give you different response, because increasing the frequency, the shorter the wavelength, and the higher is the backscatter that you receive, because you are observing what we said before, the capillary waves, which have wavelength, ocean wavelength of centimeters. So these waves are then more resonant with the transmitted pulse. So then you receive more. And this is what was observed. So you see here. So from longer wavelength to shorter wavelength, you have this curve. What is so the question is then, we have seen that oil appears as a dark patch in the SAR image, the SAR amplitude image, right? So then the question is, do we have other phenomena which also produce dark patches? So these phenomena are there, and they are called lookalikes, because they look like oil spill, but they are not. They are other phenomena. So here are some examples. So you have ship wake. So someone was asking what is happening. Is that the ship is moving, and basically the movement of the ship is smoothing the surface, and then you see this dark trail. So not very long, but you see behind the ship. Then we have natural slick due to natural biogenic activities in the oceans. And then we have the so-called internal waves. You see these, you can see that are waves, but you see the pattern between bright and dark patches, right? Then we have rain cells. So if you have strong rain over the ocean, the rain also dampens the roughness of the ocean surface, and then you have this structure of dark and white circular patches in the SAR image. And then we have also low wind speed, of course, because if you have low wind, you have no backscatter. I already have told you this several times. So then you have, for example, here you see on the rightmost picture, you have an oil spill, but there are also some low wind area. So among these lookalikes, the most difficult one to discriminate are, of course, the ship wakes, because you never know if it's a real wake or if it's oil, and also the natural slick. So the others with use of additional information. So we have said, like, using more satellites is always good. So if you have rain cells, there are coastal radars that can tell you how is the rain rate at a certain time. You can use model weather forecast data to say where is the low wind speed So if you detect something, but then you cross-match this with other sources, like the ancillary data, then you can discriminate this. So natural slick, as I said, they are natural, so you don't have anything to kind of discriminate them from oil. So which steps you can do to detect oil? And as Francesco told you, these are the steps that you also find in the SNAP toolbox. So if you go there, you download an image, there are the algorithm already developed, which is oil, and it asks you to provide some steps. So usually there are some pre-processing steps, which I think they are not implemented in, or partially not implemented in SNAP, which is, for example, you want to smooth a little bit more the speckle. I don't know who does know about speckle, because speckle is the characteristic of SAR. So you see the image appears gray and pepper. They told you about the first day. And this, of course, this randomness, it makes the detection of oil a bit more difficult, right? So what you can do, you can apply the speckle filter, which are also implemented in SNAP. There are different ones, and this helps in smoothing a bit the speckle, so reduce the speckle. Then the steps that are kind of basic and mandatory are like, from the image you want to mask the length, because on length there would be no oil that we are interested in. Then there is a fundamental step, which is dark area detection. We have said that oil appears dark, so low backscatter area, and that means you have to detect dark areas in the image. And you can do it several ways. So with applying a global threshold, or like selecting the region of interest. And then once you have this, you want to extract the parameters. So you want to have, of course, the position, you want to have the length of the oil with the coverage, the width, so basic information, and then it's passed to the final user and say, okay, look, here there is oil, it has this size, and it has these parameters, okay? And then the last step is classification, which I'm not sure if it's not there, it's implemented, probably not, but this is also a fundamental step, because, as I said, if you detect a dark area in a SAR image, does not mandatory mean that that is oil, because there are lookalikes. So what you do the classification, so oil and lookalikes. And on this, we can discuss like days how to do it. So there are several techniques. Nowadays, artificial intelligence is very, very, very well developed. So there are many, many algorithms using machine learning. You have different algorithms like neural networks, support vector machines. You have decision trees. You have multiple things. What is needed for the classification is actually a database of ground truth. So you have to classify, to train your classifier, you need to have example of oil and example of lookalikes, which then are used to train your network, and then you can use the trained network to provide the information for new images, right? And here is, near real time. I put it here. This is, normally between 20 to 30 minutes from the downlink of the data to the base station, right? So, example. These are examples that, again, so if you see the chat, you can do it also with SNAP. So you have here, in this case, it's a Terrestrial Ais image acquired over North Sea. So the bright dots that you see here, some of them are ships, some of them are oil platforms, and then you see attached to the oil platform, you see this trail of dark area. So landmask, in this case, is not applied because we are totally on ocean, so there is no land. The first step is, for example, in this case, you select the region of interest. Here is the zoom. And then the second step is the dark. So you want to detect the dark area. So applying like a threshold, say, okay, all the pixels that are below certain values are dark area, belonging to the dark area. So then you have the detections. And from these, of course, you want to extract the parameter and provide the classification. Is it oil? Is it not oil? Here is some information. You see, classical parameters are latitude and longitude of, in this case, of the center of the area of the oil spill. Provides, you can provide perimeter, you can provide, in this case, it was used neural network to classify this. What is the probability of this dark patch to be an oil spill? So in this case, it's 99%, so it's quite high. And of course, you can do it also for the other one. So now that you have this information, I guess if you go download some, there are plenty of Sentinel images with oil spills. So you can go download the image and apply the steps. So then it would be easier for you to get some of this information in your head. Yeah. So for what this can be used? So, for example, oil well locations. So, so here, for example, there are. So the movie maybe show it again. So there are 3 consecutive images that were acquired over an area. So we talked about oil seepage. So oil seepage are natural containers of oil below the ocean floor. And basically they release oil once in a while. And this is where the oil production company are interested in, because you see where you have to put your platform, right? So in this case, it's the other way around. So there was a platform there that was destroyed by an hurricane in Gulf of Mexico, and that the oil well was never kept. So from the ocean floor it's always coming oil, and from the bottom to the up, then you see oil is going up, and then you see it on the ocean surface, right? So then using multi-temporal SAR images, you can identify where this is happening. And this is basically the basic approach that I showed you before. So dark area detection on the different times of the SAR image. Then you co-register it with the GIS software, and then you see that the oil have like a common area where it always pop-ups. So then you get an information where the oil well is located, right? So I'm not sure if you are so much interested in this. So I will probably go fast and focus also a little bit more on the ship detection. Otherwise, we don't manage to finish in time. But I just want to give you an overview. So this, what I've shown you, is the classical approach using single pole. So in the morning, I told you a lot, maybe boring part about pulsar, polarimetry, but pulsar, it's very useful for discriminating oil and lookalikes, especially because to train the network or to train your classifier, you need data sets with ground truth. And the problem is not to having oil examples, but the problem is having ground truth with lookalikes, so that you know that that dark patch is, I don't know, a biogenic slick. So with Pulsar, there is a little bit more information that can be exploited. So it's not based on the classification, but it's based directly on the differentiating the scattering mechanism that are giving for oil and for sea surface, right? So, and this is the polarimetric scattering mechanism. So, with the polarimetric features that were introduced in the morning, you want to differentiate between what's so-called Bragg and non-Bragg scattering mechanism, which means on Bragg we have seen if you have slick-free, so oil-free ocean surface, you have this type of scattering mechanism. If you have oil-covered sea surface, you have a departure from Bragg, and this is the discrimination step that you want to do. And you can do it with pulsar data, right? I just give you here some of the most common techniques for either quad-pole data or for dual-pole data. So literature is vast. So if you search, there are very, very many papers about the topic. So I could not put everything here. So, but these are one of the most one. In particular, today I will focus on the dual pole, so the so-called Copperized phase difference, which, if you recall in the morning, so this is the phase difference between the channel HH and VV, okay? We have then a dual pole measurements, so HH and VV, and these polarimetric features were already introduced in the theoretical part. And from this, we can extract the so-called CPD, so Copperized phase difference. And this parameter has the distribution related to the correlation between the HH and VV channel. So you see here the plot of the probability density function of the CPD varying the correlation. So you see low correlation, so the dotted curve is very wide, so it means you have very large standard deviation when you have this type of phenomena, and you go up to rho, that is the correlation, to 0.9, or the case of 1, you will have a Dirac function, so perfect Dirac function, and you have for high correlation that the distribution standard deviation becomes smaller. So, and this is what it has been used for oil spill and lookalikes discrimination. So, as I said, so ocean surface and weak damping slicks, like the biogenic slicks, they either call for high correlation or low standard deviation, or low standard deviation. And oil-covered sea surface will have oil-covered sea surface will have either low correlation or very high standard deviation. So remind that if we have Bragg, we have high correlation, and then the standard deviation, you know what standard deviation is, right? Okay. Then you have very low standard deviation, so the spread from the mean. If you have low correlation between the channels, then you have a broadening of the distribution. So, and this is the case. So here, from left to right, so showing a SAR image. So here is left is the intensity VV of a SAR image acquired over an accident, so an oil spill. You see this large dark area, which we want to analyze. Then in the middle, it is shown the standard deviation map. So it used the CPD information, and per each pixel, the standard deviation is measured around a certain window, right? And then what you see? You see that over the oil, you have very high standard deviation. So, and on the ocean, which appears dark in the middle image, you have very low standard deviation. And this is similar. So this basically gives you an optical view of the previous polarimetric model that was introduced, right? Again, so there was a question about what is the effect of wind behind the platforms and so on. So here you see in the North Sea, the bright spots are oil platforms. On the left-hand image, it's again the intensity VV polarization. As you see, together are touched or close to the platform dark areas. So it's there highlighted what is real, what is the oil, and what is actually the wind wake. So wind is blowing from northeast. So then it creates the wake behind the platform. And what is nice about the CPD is that if you see in the middle image, so oil will still have high CPD standard deviation, but not the wake. So that means you don't need to classify this between oil and lookalike. So the lookalikes are kind of, yeah, almost automatically discarded, right? So what about other lookalikes? So I told you about natural slicks. So this is another example where you have a SAR image. In this case, land mask was applied, is in purple. And then you see close to the coast some biogenic activities. So these are like pointed by the arrow. And surprise, no. So when you see in the CPD map, this does not give you a high standard deviation. So in correlation to the area where you see the biogenic slick in the intensity image, you don't see it in the CPD standard deviation map because these slicks are so-called weak damping, so they're not completely destroying the roughness of the ocean surface. They still appear dark in the SAR image, but using the dual pole, then you see like low standard deviation everywhere, right? So this is another technique to discriminate between oil and lookalikes. This is so the most important part because you want to avoid to detect false alarms, and lookalikes are false alarms. The more false alarms you detect, the more you need to go out and check, right? So, and because SAR, as I said, it's an early warning system, you want to prevent, to send out a warning, and then patrol control has to go there and check what is happening. So of course, this has to be, so the lower the false alarms, the better, right? Yeah, so this is basically a verification of the scattering model over oil and over sea surface. So here are just the plots that shows you once estimated the standard deviation over slick-free sea surface and oil. You see that oil has a very broad distribution of the CPD, while for sea, it's very narrow CPD. While this is not happening between sea and the oil lookalike, right? Because they are, yeah, please?
You mentioned about this error, then if you have a target, okay, if you have wrong target, so we have two types of errors, wrong target, and you would like to avoid them.
So the wrong target, you mean the lookalikes? false alarms.
From wrong sleep.
Yes.
But also there is second type of error, then undetection of real target. So
Undetection of real is, for oil, is very low because actually, I mean, I said, if you are in the range of wind speed over the ocean, between 2 to 14, 15 meters per second, if there is oil, you definitely see it as a dark patch. So what can happen is, if you have lower wind speed, then you don't see anything, because even if you have oil, you don't have the sea roughness, right? So you don't have wind, so the sea surface is completely flat. So if you take, for example, an image over a lake, right, a small lake, this will be completely black. If you see a SAR image over a lake and then you spill some oil, of course this will be undetected because you have low backscatter everywhere. And the same will happen if you have high wind speed, because if you have very high wind speed, the oil start to mixture with the waves. So you don't have any more like the waves and the oil, but you will have like a mixture. So you will have roughness everywhere. That's why the oil will be undetected. But if you are in this range, you definitely, if there is oil, you definitely have a low backscatter return, and this means that in the SAR image you see a dark patch. Okay. Yeah, so some example of the same applied with different bands. Here is an example of C band, an example of L band. So just some example to show you that this approach works quite well in different bands and different, also for different satellites, which shows you that it's quite robust. Then, yeah, we did also some analysis how the CPD evolves. So the question before, how often the satellites come over, and we told you that SAR is quite flexible; it can change the incidence angle. So the incidence angle is the angle with which the antenna beam is looking at the ocean surface. So basically here you can see the plots, so which show you how the backscatter varies along the incidence angle, and how the CPD varies along the incidence angle. What was found is that in most cases, so the CPD performs in the oil detection a little bit better than the single polarization one. Yeah, so here is another example. So this was during an annual exercise from the Norwegian colleagues. So they basically do this exercise so to train in case of oil spills accident. So what measurements needs to be taken. And at the same time, there was some satellite acquisition. So you see on the left-hand side, you see SAR image with 3 different dark patches. So one was crude oil, another was emulsion, and the other one was palm oil. And then you see through the CPD, if you run the algorithm and then you perform the detection, you basically detect the crude oil, but not detect the palm oil. So palm oil is vegetable oil, so it's not heavy oil, so it's classified as lookalikes in this case. So here, to show you that you can differentiate these types of oil. Yeah, so because in the morning it was quite boring, I guess, for you, but I discussed a lot about polarimetric features, what you can do, what you cannot do. And here is just some example of the polarimetric features that were introduced in the morning, how this looks like when you have different oil types. So these are some literature suggesting to use entropy, some others suggesting using, the geometric intensity. So literature is vast, so there are pro and cons of each approach. But what was nice was to compare all these different features and see if actually, sorry. It was not me doing it. So I was sitting on my desk and waiting the satellites to pass over and get the image and process the image. So this experiment is, I guess, done annually from the Norwegian institution NOFO. Don't ask me the acronym right now, I don't remember. But they do it in the North Sea. And basically, they are training themselves to be prepared when an accident is happening. So they intentionally put some oil, or some, in this case, palm oil, and then they go with the boat and train, like you train in an emergency case. So suddenly the ringing is, and then you have to, take your way. They are training, because if you are not training, then an accident is happening, and then, of course, time is precious. So you want to, as far as possible, go there and limit the area affected by the oil, right? So this is basically, yeah, please?
I think that sounds like the most expensive model of training I've ever heard, because I wonder how they set it up. Because you have to store oil on the water and get to clean it up.
So it's a response, training in response in case of emergency. So they go with the ship, they release the oil with the ship, and then they take measurements. So they spray dissolvents, or they put these balloons, floating balloons, to limit the area, but you need to practice for it. Are there any other questions about the experiment, or? Okay. Yeah, so here, just don't want to bother you so much. So what is the message here? If you see this table, these are like the list of all the tables used for oil spill detection. And the message here is that if you see the, top 10, most of them are polarimetric features. So polarimetry, it's an added value also when you want to train your machine learning algorithm. Okay? Okay, so then I guess it's time to go to switch to ship detection. If there are no specific questions, yes?
You showed a lot of difficulties to detect the oil spills and cruise drilling. So how far are we to have strong legal, let's say, strength to prove that some ship in the sea did some drill dumping? Because I think it's basically holds no legal strength. If you, for example, provide this information, there are so many, let's say, uncertainties that someone could dispute all the reasons you showed of the difficulties of detecting them. So how do you think, how far or how close we are to use SAR data to detect with a legal strength to detect the oil dumping corridors?
Yeah, so just as a remark, so if you recall, so there were this MARPOL, that is the worldwide convention about preventing oil over the ocean. So in these limits, that means that if you have a larger, so you are spilling more than what is there, so you definitely see it on the SAR image. The problem is that even if you detect an oil spill, so you have like the ship and the trail, large trail, long trail, behind the ship, which is oil, and you say, okay, this is oil. Unfortunately, you cannot go to court and say, okay, you are the culprit of this oil spill, you have to pay for the damages. Because first of all, only with the SAR image, you have the detection of the ship, but it's not an optical image. You have the detection, but you don't see the name, you don't have an identification of the ship, right? So what is done by EMSA, so usually you have this, and then you integrate with what I will show you now, what is called automatic identification system. So this system is a tracking system of the ships. So, and when you have you have the SAR image, you have the track of the ship, and then you match, like the example I showed before. Even in this case, I think it's not yet accepted that you can, because with the AIS, you have the name of the ship, you have the company, you have the so-called MMSI, so you have a specific, so you identify the ship and you identify the company. But what is done, actually in court, you need to have in situ verification. So this is what, for example, that's why I said, what EMSA is doing, they offer the service to the member states. So when they detect an oil, they can identify the ship with AIS. They send this information to the member states, say, look, here's something happening. Please go and check, right? The problem is that, if you read through the EMSA reports, you see that through the CleanSeaNet, there is a decrease. Since the CleanSeaNet is there is a decline of number of oil spills that have been detected with SAR, because if you have a service, you think twice before doing an illegal thing, right? So if you know that, then you can be called on court and you have to pay. So for the Deepwater Horizon, for example, so in that case, it's an accident, and I think it's British Petroleum that had to pay for the cleaning of the beaches, of all the damages, and so on, but for this routine operation. So CleanSeaNet will send the information to the member state, and then the member state patrol control needs to go there or fly with the pollution airplane and then stop them, because you have the so-called oil record book. So there you need to, so the captain has to say, okay, how much oil there is there, how much was the charge, and if you see a mismatch, then you have a court proof. So it's as I said, so SAR is like the first step. So it's the early warning system, because from there, then of course you go all the steps through. So up to the, how to say, check that everything was actually happening.
But what about the regions where there are it's quite cloudy and so on? So I understand that you use this.
Clouds are not.
No. I mean that's the question. So you need this one. So they use this one like SAR data, like early warning, to then go to check, like for example, high resolution optical image as well. I guess yes. Like does.
Yeah, they do this. Yes.
So, and then like what's the solution when they cannot get the, so for example, you detect the OSPO possibility, and then they check for the optical imagery from, for example, from Maxa or whatever, and then if it's basically cloudy and so on, so then basically it's sort of no one can do anything, or then it's just.
No, what I mean is that the let's say the information you have from SAR is, okay, you know the location, you know the latitude and longitude, you know the extent more or less, right, of what is happening. This information is passed through the national pollution control. I don't know here which entity. So in Italy we have Guardia Costiera.
Coast Guards.
Coast Guards, right? So the Coast Guards, then they need to go over there, or if the country has a airplane pollution control, then they can fly over and check. So you need to check in situ as well. So let's say to identify the culprit and then bring this to court.
We did a similar course to this, just about oil spills and ship detection to EMSA with SAR. It was 20 years ago. And already at the time they were using, they didn't have the Sentinels, of course, there was not Terrestrial Ais. They were using Envisat plus Radarsat. They were combining European and Canadian radar information.
Radarsat is still used by EMSA.
Yes, and already at that time, just with these two systems, they were doing that routinely, and they had very often radar acquisitions. And as soon as they suspected that it was an oil spill, because you cannot be certain 100%, because there could be other artifacts with oil spills.
Yeah, we already discussed this.
As soon as they had suspects that it would be an oil spill, and then they saw also a ship nearby, then they immediately informed the member states, and they would send the coast guards to the place, and then they could...
this is the routine operation that is done.
And they were doing with all the member states of EMSA.
I just want to mention one point that is a critical point. And although, as I said, if you read the reports from EMSA and CleanSeaNet, they show the statistics of how many satellite SAR images were acquired, how many oil spills were acquired over the time, and then you see a nice decline, right? But keep in mind, so we are using SAR satellites that are polar orbiting. So you have passes over Europe either in the morning or in the afternoon, and in between, you don't know. So you see this decrease, but you don't know in between what is happening. So that's why more satellites is the way, the more the better.
So we should not inform the ships that there are passes only in the morning. They could decide to clean the reservoirs at noon.
I'm afraid that maybe, I mean, if they do these illegal things, they might get informed of what EMSA is doing. And
some people could decide to attend these courses just to overcome the capability of the satellite.
Yeah, but of course, besides the satellite monitoring, of course, you have the standard routine operation monitoring, like the Coast Guard and other things. So it's, of course, not everything based on satellites, but they are of a great help because, as I've shown you, ocean is quite large. So, other questions about?
Some minimum size, usually you can say that it's too small to detect, or for example, the ship might just let out a little bit of bilge water and then again.
Okay, actually, if it's a little bit, what you mean little bit, it's then probably not an option. Usually, oil, so we did some experiment releasing some biogenic oil, and it was like 10 liters or something, and in 10 minutes, because what is happening is that the oil spread very fast, stretch very fast. So you have different processes that you can read in these slides about SAR oil spill interpretation. You have biodegradation, you have the spreading, so there are certain phenomena that are fast, like spreading and moving, because if there is wind, current, oil moves fast. And then there are other processes like biodegradation, emulsion. This takes a little bit longer, but I mean, you can do the experiment at home. You know, as soon as you put oil on water, you have like a very fast spreading of oil. And also because the oil thickness, we are talking about micrometers. So it's very, very, very thin layers over the sea surface. So other questions about the topic, or we can switch to ships? Okay. So, bit of motivation. So why we want to have ship detection? This is mostly, yeah, should be already be clear to you. We have large oceans, so the area to cover is large. And if you see the worldwide ship density map based on the so-called automatic identification system data in 2021, then you see that besides you can see the major routes between the continent. Please. Yes. Yep. Yes. Okay, I was a bit fast here because we are running out of time, but this is a study where basically we compared the so-called standard features, which means standard you just have a single pole image where you extract the size, the spreading, the length, the area, and the only radar parameters that you have there is the radar backscatter. So with polarimetry, you have more features, right? So all the features that I introduced in the morning, you have the CPD that I show some example, you have the correlation, entropy, alpha. These parameters can be extracted from dual pole. And what we did here, we said, okay, are they really features that help the classifier in discriminating the oil from lookalike? And the answer is given by this table here. So what is here, you see the top features are the one that gives you more information about discriminating. And these are like, they're abbreviated, but they are like geometric intensity, the polarization ratio, span is the total power, then you have the force, is the power ratio of the objects, and then you have anisotropy, the contrast. So contrast is usually, they're defined as the ratio between the backscatter you measure, for example, over the dark area and of the surrounding sea surface, right? And then you have the standard deviation of the object. You see, all these parameters are all polarimetric features. I guess the first standard parameter is the max, what's called max underscore contrast. So this is what I said. So the contrast is the ratio between the backscatter that you measure over the dark area and the backscatter you measure from the surrounding ocean. But all the others are top 10, so you have 9 polarimetric features and 1 standard. So this was kind of study that proved that with polarimetry you help your classifier training better. So I don't know how many of you are in the AI topic, machine learning. So machine learning, of course you need a lot of data, first of all, to train the network. But previously, before the convolutional neural networks, there was the so-called features engineering. So people were interested, okay, I want to reduce the number of features that helps my classifier, because in some cases, you have more information that does not help your classifier, actually makes classifier more confusing. So that's why here we did this study. So here, I guess, we use a support vector machine as a background classifier. So we classified the things, and then we said, okay, which features are more relevant, okay? And yeah. Okay. No other question on oil? Okay, so how many of you already know about AIS? Because if you already know, I will skip some slides. Nobody, okay. So what is AIS? So actually this system was kind of invented for vessel collision avoidance. So, and basically works exchanging messages between ship and ship and shore-based station. So basically, if you have your own ship and you have an AIS receiver, you receive the messages from all the ships, and then you can integrate this information in your pilot cockpit, right? And then you see all the ships around you. So these messages are basically sent and received by the transceiver of the AIS using radio waves. So basically using the VHF, so very high frequency channel. There are two channels that are dedicated to AIS. So you see there the details about frequency and the channel name. And basically it works on what is called transmission protocol. So the base is this time division multiple access protocol, which basically means that you use a slot in time to send your message, right? There are different classes of AIS. So just for your information, the most famous, most known ones are so-called class A and class B. So the class A are mandatory for large vessels. And class B are receivers that are for small vessels. So the difference is that class A is a little bit stronger in power. You have the possibility to have a display which shows you the information about the surrounding ships and so on. So each minute is divided in 2,250 time slots, right? And because we said we have two channels, we have 4,500 time slots available. So the ship, so the AIS transponder allocates a time slot to say, okay, I use this time slot to send my message. How many message types you have? There are 27, so I don't want to bother you with all of them, but two are basic for us, right? So there is the so-called position message, which is named 1, 2, 3, 4, 18, 27, blah, blah, blah. So this is differentiated between class A and class B. Don't worry about it. And then there is the static and voyage message. So the position message, it includes, so it identifies the ship via the so-called MMSI, then you have the latitude, you have the longitude, you have timestamp, you have the speed over ground, and speed and course, heading, and of course, this information are given to the AIS transponder by the other ship's instrument, like from the GPS, from the gyroscope, and blah, blah, blah. And then you have the static and voyage message. So these messages provides the name of the ship, which type it is, which dimension, the length and the width. It gives you the estimated time of arrival. So very, very similar is what you see also for airplanes. So you have, for example, flight radar. You go there if you want to see if your flight is delayed. You go and see the track. So it's the same. You can do the same You go to websites that shows you live AIS messages, and then you see where the ship is, right? The difference is that this static information is compiled by humans, so by the operator. So the captain installs the device and says, okay, my ship name is this, my length of the ship is this, and so sometimes it's not that reliable because it's compiled by a human, we are prone to errors. So we have seen like strange things happening in some AIS data, but the other question is how often these positions messages and static messages are sent. So this depends on the status of the ship, if it's a tanker, if it's moving, and it ranges between 2 seconds and 3 minutes, while the static messages are sent independently each 6 minutes, right? So basically, this information is what was used to generate the previous map showing you the density of ships around the globe. So who has mandatory an AIS message, an AIS receiver transponder? So all passenger ships, they are mandatory, required to have an AIS. All the other ships which are larger than 300 gross tonnage and doing international voyages, and cargo ships larger than 500 gross tonnage, also if not engaged in international voyages. This is the general regulation given by the SOLAS, safety of the seas or something like this. And of course, there are additional regional regulations, like the EU, for example, put a mandatory IS on board fishing ships that are larger than 50 meters length, quite important because of the illegal fishing, and also for commercial US flagged fish ships, which are larger than 65 meters. So what are the limits of this system? The limits is, of course, given by the line of sight radio wave propagation, right? So 2 ships that are far away, more than 40, 50 kilometers, will not see each other. So will not receive the message because of the curvature of the Earth. So the radio propagation will not reach this. So as a rule of thumb, so if you have a base station, of course, this line of sight depends on the height of the receiver. If you have like a base station on about 100 meters above the sea level, you have a coverage of around 35 to 40 kilometers. So this is so-called terrestrial AIS. And this is the limit in the horizontal range of AIS. Fortunately, so it was also discovered that AIS messages can be received by satellite. So this is called satellite AIS. Of course, the satellites are orbiting in a LEO orbit. And some issues related to the satellite AIS is that from satellites, then you have a very, very large coverage. And we have seen that you have limited time slots that can be allocated. So sometimes you have this conflict in messages, which nowadays there are companies that are building satellite AIS. They are doing the processing either on board or on ground and can avoid these conflicts. And of course, from satellites, you have like not a real track. So you have like position now, and maybe the next position will be like in 1 hour because the satellite is passing in 1 hour. While the terrestrial AIS, you have the track of the ship, right? Kind of in real time. So for water use, so there are different use. So what I want to point out here is, as we said, this information is very precious for as an added value for SAR, oil spill, and ship detection. Because what we said before, so if you detect the oil, you can detect the ship, but you want to identify the ship, and you can merge the AIS information with the SAR satellite, and then identify the ship with the AIS. And just as a reminder, so the captain of a ship, of a tanker, is not allowed to turn off the AIS unless there are some security, safety emergencies. Okay, otherwise, easy to turn off, spill the oil, go away. It's not like it works. So you have if they switch off, they have to justify why it was done. So how the ship are detected? So here we have a ship over the ocean, nice ocean waves, surface. We have the satellite is acquiring the image with a certain field, let's call it field of view, so it's called incidence angle. Then we already know that the ship is a metallic structure, right? And everything that is metal reflects well the radio waves, so that's good. And because the ship and the ocean are kind of creating this dihedral, so you have like very strong double bounds of the transmitted electromagnetic waves through the bounds between ocean, ship, and back, right? You might have also direct reflection from the ship itself because it's a metallic structure, and then that's why in the SAR image also you've seen before, you see very bright dots. And of course, we have the surrounding ocean. We have already discussed about it. So we have, in this case, VV and HH polarization. So this is how the backscatter of the ocean develop with the incidence angle, so how you look the ocean surface. And if you see, like, if you are acquiring with very high, so very large incidence angle, then the arrows there points to the curve of radar backscatter that is low. You have high backscatter from the ship, and this is why you have very strong returns from the ship, a very dark area around the ship. So that's single pole detection. That means you basically are detecting bright spots in SAR image. You can do it basically saying, okay, take the amplitude image. HH is usually preferred over VV because the contrast between the ship and the ocean is a little bit higher, because we have seen. So in VV, you have higher ocean backscatter. And then see and say, okay, whatever is larger than this threshold is a ship, right? So again, as a reminder, if you go in SNAP, there is a ship detection there, you can do it. So, and it asks you, okay, what threshold you want to set, right? So it's basically this. So then what happens when you have a lower incidence angle? We have said that SAR is flexible to cover the same area with different geometric view. You can steer the beam of the antenna and acquire the image with a lower, with higher incidence angle. So what happens in this case is, of course, in this case, you reduce the double bounds a little bit between ocean and ship, so you get a little bit less return from the ship. And what it happens is that you get actually more backscatter from the ocean. So you can even, if you go very steep, you get like specular reflection from the ocean. So you get very strong backscatter. So that's why here you see that you have still the ship visible, it's bright, but the background is also higher, right? And in that case, you have a little bit less satisfactory results if you say, okay, detect everything that is bright, because you might end up in detecting pixels that are actually oceans. How ships looks like inside image. Here I show you some example of 3 types of ship. So the columns are like the same ship that has been seen by the same satellite, but using different modes. So if you remember, there is ScanSAR, large coverage, low resolution, up to Spotlight, small coverage, high resolution. And then you see, of course, for small, medium, and large ship, of course, the resolution plays a role, right? So less resolution, you might end up in not detecting the ship. Then the question is, what is the minimum ship length that you can detect, right? So some researcher from Canada, they developed a tool which predicts what is the minimum ship length versus the incidence angle. They did it first for C-band, so basically the radar satellites. They extended also to X-band. And the plots that you see here, so the blue is for C-band, and red is for X-band, and solid line and dashed line are for 2 different resolutions. So we are talking about low resolution here. So the continuous line is about 40 meters, and the dashed line is 18 meters. And then you see that, so according to the previous theoretical model, that as far as the incidence angle increase, then the minimum ship lengths decrease. So in the y-axis, you have the minimum ship length. This is log scaled, right? So higher incidence angle is better. Lower incidence angle is not so good, right? And here it's nice because then you can compare also the frequency. So you can compare the C-band with X-band, where it shows that X-band, it performs a little bit better than C-band, and this is because of the wavelength. So wavelength is a little bit shorter, smaller, so you have a little bit higher probability to detect a smaller ship in X-band than in C-band, right? Here, the plots are the same, more or less. This is a study to estimate, again, what is the probability of detection theoretically with SAR, depending also on the wind speed. And in this case, for different ship classes, we have small ship that range from 1 to 25 meters, medium ship 25 to 150 meters. Sorry, that's a mistake there. So that's large ship for length larger than 150 meters. So what I want to point out here is that, again, so wind speed here plays a role, right? Because if you large ships, you basically have almost a certainty with a resolution of 3 meters to detect this ship. So independently on the incidence angle, independently of the wind speed, you see the right-hand side, you see probability of detection is red almost everywhere. As far as you move to the left, right, so going to the small ship, then you see that when the wind speed starts to increase, then you have a lower probability to detect the ship. That's because, as we said, higher the wind speed, higher the backscatter from the ocean, then the contrast between ocean and ship starts to decrease, right? So here an example of about what is the role of polarization, right? So we have talked about all the morning about SAR polarimetry. So here you see like a small part of a Google Earth image where there are 2 small platforms. These are about 8 meters and 4.5 meters. And here you have the single pole image. Then you see that both target with single pole, high resolution, 3 meters, they are giving you a strong backscatter response. So you see the white blobs in this red circle. However, when you do polarimetry, remember that we said there are side effects. So one is reducing the resolution, and here you see it. For example, if you have a look at the same scene acquired by quad pole, in the quad pole mode, you see the comparison between single pole and quad pole, and then you see that the upper left target is actually not visible. So it means the resolution is low and you don't get information. And the same is actually happening if you have a look at VV, because in polarimetry, we said you have more information, you have HH, you have VV. In that case, the upper left is detected, but the target in the middle is not. But the good news is that with polarimetry, you have also the cross-pole channel, which shows you that both then are detected. So yes, you reduce the resolution, but you gain information about the scattering mechanism that are in place, right? So that's the message. Questions about SHIP, differentiation within wavelength, minimum ship size, polarization? All clear, all fine, good. Okay, what are challenges? So the first challenge was mentioned in the morning, whatever it moves is not a friend of SAR, because a ship, they can be a tanker, but they also move. And when you have a component, the radial component of the ship velocity, these produce the so-called train of the track effect. That means the ship will be geographically displayed. So it's not in the real position, but is an effect due to the SAR focusing algorithm, right? So this because the component of the velocity creates a Doppler shift, and the Doppler shift in the SAR image, in the image formation, you're seeing that everything is static, and this Doppler shift then produces this shift. So if it's toward the radars, it goes up. If it's away from the radar, it goes down. And you see here an example where we have in the background, we have a SAR image and a moving ship tracked with the AIS. So this these cyan arrows doing this snake, it's actually the AIS message received by sent by the ship. And then you see that the actual position of the ship is more than 200 meters away, what is as imaged by the ship. Of course, this has an impact on the parameter estimation, because you want to retrieve also the location of the ship, right? You detect and locate and give this to a GIS, to any system to show the position of the ship. Then the other effect is related to the component of the velocity of the ship along track, right? So who does know about along track, azimuth, across track? You know, so component along track of the ship creates a so-called defocusing. That means the ship will appear stretched, right? So it's not focused anymore, but the backscatter is a little bit spread along track, so in azimuth. And this, of course, has an impact on the ship length estimation. So the example there's a ship, the length is 68 meters. If you load the image with a GIS software and then you measure the length, then you see that the ship actually appears like 85 meters. So this is, of course, a problem. And you see the plot that shows you that the relation between ship length estimation versus the true ship length given by the Ais. So we have there root mean square error about 17 meters. Another effect is the so-called cross-like radar response. So of course, ships are large and they have large dihedral structure. And we've seen that whenever we have a dihedral, you have a strong double bounce. And what happens is that you have the signal that is spread in a cross-like way. And this, of course, impacts the estimation of the ship's width, because you detect all the pixels belonging to the ship. You also detect these bright lines in the y direction, and of course, your ship will be estimated with the wrong width, right? So of course, all these are effects that can be mitigated with some image processing techniques. Another problem is so-called Azimuth ambiguity or ghosts. It's a tough topic, but basically because the SAR is sampling the Doppler spectrum in a finite way, you have all the signals that are outside the process bandwidth to fall down to the inside the process bandwidth. So basically, say it very easily, you basically have real ships and ghosts. So these are like artifacts that you can have inside image. And here you see an example of real ships, and the arrows points out to azimuth ambiguities. So these are replicas that are there, but if you use simply the detection algorithm, okay, detect everything that is above a certain threshold, of course you will detect also these ambiguities, right? So, and of course, this has a strong impact on the performances, because if you detect ghosts, you are increasing the false alarms. So these are not ships, are ghosts. So, and of course you want to avoid this. Okay, this is just another example that this can happen not only from ship, but also from land. You see strong replicas of the city over the ocean. Here is for Terrestrial Ais. You see it. Oh, sorry.
How is it possible to deal with the azimuth ambiguity? Like, how do you filter out the exposure? Something like calculation?
I will show you some example in a minute. So just wait a little bit, then we go to the topic, because it's something that I try to address. Okay, so basically it's the answer is here. So these are this is the workflow of the steps. So parallel to what we have seen for oil spill, the steps that are needed to detect ships on SAR images. So here it's the workflow. Most of the steps are, again, also implemented in SNAP. So you can try masking the land and detect the ship as well. So you are encouraged to go there, download some images, and test yourself this. So we have several steps, right? We have so-called basic step, a more advanced step. So of course, the first step is detection or pre-screening. So in the green, there are different techniques. You can use global thresholds. You just have the whole image and say, okay, everything is above this is a ship. The work is fast, but performances are not so good. And then you have the so-called Cfar detector, which is very used in radars. So it stands for constant false alarm rate. We will see how it works. Then you have the step that is advanced, so about refinements of the detections. So try to mitigate the problems that we saw before, like the smearing in Azimuth or the cross-like features that you have on the ship. Then you have the land mask, and then of course you have the parameter extraction. So you want to extract the length, the width, the heading. In some cases you can extract also the velocity. Not so easy for using single pole amplitude image. So, and as image product here, you have like different modes: ScanSAR, strip map, spotlight, and usually you use so-called ground range detected product. So if you go in the HISA hub and you want to download some Sentinel image, you see there, it asks you, okay, which product level you want, and you usually have like the acronym SLC or GRD. GRD means that you get a product that is detected. Detected in this case means that you get only the amplitude without the phase of the SAR image, right? I'll show you some example of ship detection using also the phase later on. And then ancillary data here are like some annotation file. So you need to mask the land, an external data set, possible the Ais data stream, then that is used to identify the ship in the final product. So I guess in Snap, the Cfar should be implemented. Azimuth ghost removal, I do not guess it's implemented. And also refinements, I don't think it's implemented, but you can do it with the pipelines. So we will show you how it's done this. Oh, battery is low. Yes. Yeah, just a second because the battery. Yep. So these are the steps. Just want to explain a little bit how the Cfar works, because this is the most used algorithm for ship detection. So the concept of Cfar is that you want to keep the false alarm rate constant, right? And you see here the histogram of the amplitude image, and basically you want to change the threshold in a way that the false alarm is kept constant, because as we see, the radar backscatter over the ocean, it changes, so you have different distributions. So what you want to achieve is actually what is shown here. So you have the input image, this is just a small snippet of a SAR image with a ship, and you want to have a nice detection mask, which it's a binary image. So 0, it's given by ocean, and 1, it's given by giving two pixels that are belonging to the ship. So of course, this detector is, compared to the global thresholding, is a little bit more complex, and it's pixel-based. So you want to analyze all the pixels in the image, and when you go with very high resolution images, the number of pixels you have there, or with large coverage like Sentinel, you have to run this algorithm quite a lot of time. So it could be computationally expensive. Yeah, so this is what you have. You put the threshold there, you have the detection, right? Yeah, so here is just once the threshold is defined, so probability of false alarms is actually the area below the probability density function for a fixed threshold. So how it works, I said, so it's kind of nested sliding, moving windows. So you have the so-called, here you have a background window, a so-called guard window, and target. If you go in Snap and you want to try yourself, it will ask you, okay, how large is your background window? How large is your guard window? And how large is your target window? So this is done because the background window is used to estimate the ocean, let's say the ocean clutter, right? So because based on this, you want to detect everything that is not ocean. The guard window is there to guard, so to avoid that part of your target goes inside the background window and pollute the background estimation. And then you have the target window. So it's what you compare with the values of the background window. So and then you have to run these along all the image, right? So here it shows you how it works. So you do step by step. You see that this histogram is changing. It's changing also the threshold. It goes to the target. Then the target, you set the threshold that follows the probability of false alarm that you set, and then the target is detected. Then there was the idea of Cfar iterations. This is the case when, for example, we have this image, right? Then we have our Cfar set up with background window and guard window. So then you have your threshold. Everything that is above this threshold are chips. So you see the results on the detection map at the first iteration. But you should notice that the chip that's actually there is missing. And is missing because there are 3 chips, right, that are polluting your estimation of the background. So the idea of iterative Cfar is that you have run the first iteration, you have your map, and then in the second iteration, you go back, but you are excluding the previous detected targets. So then you have a better estimation of the background. So you see the threshold before was too high, right? So that target did not have enough amplitude or strength to be above that threshold, so was not detected. In the second case, so because you are estimating better the background, then the threshold is lower, and then in this case, you have the detection of the missing chip. Here are some examples of algorithm using single loop complex. I don't think these are implemented in Snap, so if you don't mind, because we are running out of time, I will just skip this part and go directly to some example of dual pole. So here the approach is using reflection symmetry. So we are discriminating ships and ocean surface using dual pole, copole, and cross pole channels. So dual pole polarimetric data. Some examples here for Terrestrial Ais in X-band, 2 datasets, there are some ships there. You can read all about it later on. What I want to show you is that you have the so-called R image, processed image for both datasets on the left and right. and then you see the detection. So you see that the ocean follows the reflection symmetry approach, which makes the ocean totally black. So this is something good if you want to detect bright spots, because the black, so the lower the ocean backscatter, the better you can detect the ships. Yeah, so this was an example where we use also dual pole, and to validate the algorithm using this small control boat. Here you see a picture was something like 4 meters. And here is a 3D scattering plot of the ship, which was the strength in HH, the strength in HV, and then combining HH and V in amplitude, and also combining HH and VV with phase. And then you see on bottom right said that this peak is much higher than the ocean surface, which is, in that case, color-coded as blue. So that helps a lot for the ship detection, right? Yeah, so I don't know about how you know about rock curves. So this was just to show you that comparing this algorithm with standard technique, we could get better performance. So we could increase the probability of detection, keeping the same probability of false alarms. And the algorithm works in different frequencies. So it was tested on L band. It was tested also in C band with quite good results. And to come back to the azimuth ambiguity, so here's the slide that I want to show. So either you, in the step where it was in the workflow, discriminating the azimuth ambiguity, you actually make use of these relationships. So we said that the azimuth ambiguity are ghost replicas displayed in azimuth direction, and they have a fixed displacement. And displacement is given by the equation here. So what we use, you detect everything, and then from the detection, you check, okay, do I detect anything also from this ship on top or above? If yes, if it's exactly at, like in this case, you see, in this case on the right, we have this building that is showing in the ocean, and it's fixed, it's 3.6 kilometers approximately. So if it's that distance, then you remove it. So this is part of the filtering. Another technique to remove azimuth ambiguities is using quad pole. So again, this was how quad pole works. So I just want to show you the example. So here we make use of the both cross pole channel in quad pole image to discriminate the ships. Actually, what we do is we create, we create so-called ambiguity-free HV image, because according to the rules here, so VH and HV channels are equal for targets, but are opposite in phase for ambiguities. So we make use of this polarimetric feature to beforehand just remove the ambiguity and have an image without ambiguities. So here in an example, you see a lot of strong ambiguities over the ocean, which are not detected, as you see, either for land and for ship. And another example that shows the effect of different polarimetric features. So you see what is highlighted in red is what is using the HV-free image. And if you directly compare with the image above, you see that all the replicas of the Gibraltar Island are actually not there, right? So then when you do your detection, you are actually detecting only the real ship and not the ghosts. So here yeah, just bit comparison between this method with other methods. So literature is quite large, also dealing with polarimetric discrimination of azimuth ambiguities. And I think it's time to close, right? I just want to thank you for your attention and show you here a nice movie where we combined satellite image with radar-based, so-called VAMOS wave radar system. And you see also the Ais of this ship that are running, and then you see the same on the radar. So what was here, what this dot that is appearing there, it's actually, yeah, you see it there. It's actually a small rubber boat that was released by the mother boat, that was what is named here Bayreuth. And suddenly, because this yellow arrow was coming up, so they were afraid that there would be some collision. And then you see suddenly that this small dot that is tracked with GPS is going to the mother boat that is given by the Ais by this red arrow. So that's everything I wanted to tell you about oil and ship. So there are many more other topics about marine applications, but those are the ones that I know better. So if there are questions.
Yeah, anyway, we don't have much more time. I think the course was quite dense. We tried in 1 week to cover many different applications. It was not possible to cover more or to go in more detail for each application, because you have seen that especially for items like radar interferometry yesterday, you could have just 2 weeks or 3 weeks, of course, just about that. So it's a real challenge to try to pass you the information about so many different things in 5 days. The real purpose of these courses is, of course, is not, we don't expect that you will become expert about each application just with this course. I think, at least for as far as I'm concerned, when I did similar courses in the past, the real purpose was to understand whether I liked some subject, and I found that it was applicable to my to what I was doing if I wanted to get further into it. So now you have the information, you know who are the experts, or at least some of the experts. So if you really decide to go into one of the fields that you have seen, of course you have to continue studying on this. We have told you about many other opportunities that we have also online, but you know the experts, so you could decide to contact them and to have further experience and training on the subject. So thanks, Domenico, for accepting to come. I know that you had challenges also with the flight from Germany. Yes. Finally, we made it. Otherwise, it would have been also a remote presentation. But thanks God you managed to come. So thanks again. And
yeah. Of course, I will be around, I guess, until lunchtime.
And maybe you have given your email contact to the students in case they want to contact you?
Just approach me, we can discuss.
Yeah. So now this part of the course is finished, the academic part. Okay, I think you have a little present for Domenico.
From Ministry of Education and Science of Austria.
Oh, very nice of you. Thanks.
Yeah.
Thank you. Thank you.
So this part of the course is finished. We still have this afternoon. Wait, don't go away because we have just 10 minutes more now. So this afternoon will be different. You will see, okay, some Jupyter Notebook examples. Amalia and Magdalena Firczyk from Poland, working in ESA, will show that to you. You will also have some presentations about Latvian projects in Earth observation, I think by experts here around. So that will allow you to connect what you're seeing with real projects done in the region. So it should be interesting. There is something more. Okay, first of all, Amalia will just tell you, I think she put in the chat some additional resources related to radar for oil spill and ship detection. She will tell you something more about that. And then after that, a colleague from ours, from ESA, ESTEC, Karol Brzostowski, from Poland, working in ESTEC. He's the country desk officer for Latvia and also for Croatia and Slovenia. He will tell you more about opportunities in industrial, foreign companies and in the industrial field.
Okay, yes. So because what we saw this morning is theory, no? So we wanted you to have the chance to practice a bit. And in the chat, you find two things. There are two webinars coming from the Rus Copernicus project. So the webinars go from the very beginning on how to acquire the data and download them to the theory behind and processing it in Snap. And they cover oil spill mapping and ship detection without the AIS part, though. And the second thing is one of the modules in the SAR MOOC. So in the SAR MOOC, you find all the theory about SAR, and you can personalize your path, choosing the modules that you like. And there is a module about water applications, which includes a part about maritime applications with an exercise about oil spill mapping. So I left you the links in the chat.
All the lectures this week have been recorded, so we will try to put the videos somewhere. Either will be on the web page of the course or on the ISA web page. So this is something we still have to decide, so that you can go through the lectures again if you wish. And I think you will also get all the presentations.
Yes, of course.
Yeah. So maybe Amalia, you could add the information you put in the chat and the last slide of Domenico's presentation, because since it's related to.
Yes. So I think we will add this to the thank you email where you will receive the certificates.
Yeah. Okay, so now Carol can say something about industrial projects and opportunities.
Yeah, good afternoon, everyone. I know that you are probably hungry and waiting for lunch, so I will be quite fast. I will try to be quite fast, but I think it will be quite useful information for you. As was mentioned by Francesco, I am country desk officer for Latvia. I am working in such section which is very complex name. It is New Associate and Cooperating State section. However, our section is dealing with new countries in ISA. When the country is approaching ISA, the full integration process is very long. It is 20 plus years from the beginning to the end. Latvia is more or less in the middle. Latvia is associate member. So in the beginning is a cooperation agreement, then is PECs, then is associate membership, new member state and full member state. So we are in the middle. And our section is supporting the countries. And we are working like that each country has separate country desk officer, so person dedicated to the country. And we are trying to support country on different levels, starting from delegation. So I am dealing a lot with Kaspars, probably you know Kaspars, Angelina as well, and all the, let's say, political environment. Also, I am supporting entities in this integration process, because as you know, working with ISA is not always very easy. I hope it is nice in the end, but not easy, especially in the beginning. So I know more or less all, I believe, entities in Latvia which are doing something in space or wishing to do something in space. That's why I would like to take this opportunity to introduce myself to you, because I know that many of you don't know me, I don't know you. But in case you will have any questions related with whatever topic related with space or ISA, you can always approach me, you can send email. And yes, I would like to share 2 slides or 3 slides, because if it will be feasible, this one, yeah? Oh, yeah. Because as was mentioned by Francesco, okay, the aim of this meeting probably was to get some knowledge, of course, which will be very useful, but in the end, you must do something with this knowledge, because knowledge for knowledge is not very useful in the end. And so, from my perspective, how you can use this knowledge, it depends, of course, if you are from industry, from academia, or from administration. There's different ways. However, all these 3, let's say, kind of entities could support, or let's say, could be included in cooperation with ISA. If you are in administration, it doesn't mean that we don't want or there is no chance to cooperate with us. However, I believe that this cooperation between you 3, I mean industry, academia, and government or administration, is very very useful and very beneficial for everyone, especially in Earth observation domain, because as it was mentioned many times probably, and also it will be mentioned, there will be some examples probably from Dainis and all people from Latvia. Such cooperation is very useful. I mean, industry delivering something which is useful for government or administration. I don't know why I cannot share that. Not really. Okay, if there is a problem, there is. Yeah, perfect. Okay, so I will give you one example how you can start working with ISA. So of course, through cooperation with already experienced people, you can discuss with Dainis. There is few entities already from Earth observation domain which are working with ISA. For example, Institute Foundation of Environmental Solutions, Baltic Satellite Solutions Services, sorry, and MIX. For example, these three I can mention, they are running quite a lot of contracts with us, probably around 10 already. So probably it will be direct contact with people from these three entities will be very useful. And I believe some of these entities already try to approach or will try to approach you as a potential customers if you are, for example, from administration. And I would like to mention one thing which is called RPA funding scheme. RPA is Requesting Party Activities Program, the program dedicated for Latvia. You've got like national element when the competition is only limited to Latvia. The next call will be open in September this year, but of course I will not go into details. On the 12th of September probably we will have briefing. So briefing means that we are coming here and we are explaining all details regarding this RPA call. What I would like to show you, sorry, maybe I will change this. Yeah, I will show you only. Okay. Okay, doesn't work. Okay, I cannot open the next presentation, but yeah, this is the most important. I mean, in this national call, you will have like list of potential activity types which you can submit proposals under with. And I think this is the most important for you, and this one. Type F is space applications, space downstream applications. So exactly what was explained today, all this knowledge you can try to use to create some downstream applications related with Earth observation. And I believe after the launch, there will be some examples of such applications coming from Latvia. And exactly most of them is coming from RPA call or previously PEX call. So not to go further into details, 12th of September, if somebody will be interested, you should be probably invited by Kaspars because it is delegation. And then we are coming here and we will discuss this opportunity in more details. In the end, I hope, yeah, there is some, this is me. So you can take picture and in case you will have any question, you can contact me. This is my manager. However, I should be your first contact point. This is not important for you, yes, because it is not. I didn't expect that I will have presentation, so I didn't prepare presentation for that. Of course, you can always contact Kaspars, Karolis, this head of delegation, and the second person which you can try to contact is David Stebelis. I don't know if you know him. If not, you can ask Kaspars or people working with ISA. Already, David is your country industrial coordinator. So, person living here, he is Latvian, which he should support you in, let's say, also cooperation with ISA. Okay, if you will have any question, I will be here like for probably 1.5 hours. Just approach me. In case, you can always send me an email. And I hope we meet in one of proposals which you will be teaming with some industry or academia. Okay, thanks.
Thanks, Carol. So take the opportunity to talk to Carol if you have ideas about opportunities or questions. And I take the chance to say goodbye to you because I'm leaving now for lunch, so I will not be here in the afternoon. It was a real pleasure for me to meet you and to work with you. I hope it was also nice from your side. And this afternoon, please fill the feedback form that we have, because we need feedback in order to improve the next courses and to know if something was not according to your expectations. We will use it for the next courses, so please do that. That's all. We don't have the ceremony, the closing ceremony with the certificates, because now it's no longer in hard copies, so it will be sent to you by email, I understand. Normally we had this ceremony for the last 10 minutes of the course, but now unfortunately everything is done electronically, so that takes part of the charm of for my taste. All right, good. So thanks again, and enjoy your lunch, and see you next time.